Welcome back to High Performance Computing, Lecture 2, Parallel Programming with MPI, and our second part of the lecture, which is really looking into much more of the parallel programming basics. In the first part of the lecture, we really understood a little bit the basic concepts of MPI. We understood why parallel computing is important. We derived this problem from very complex and large scientific and engineering applications that really require high performance computing to do complex computations. And these are in different domain specific areas, from neuroscience up to computational fluid dynamics, from machine learning even, what we have seen, basically also up to elements of how you manufacture an aircraft and how you can actually understand the stress of the materials, the turbulence that is happening in the turbines, and so forth. And we then came to the idea that this parallel computing is really, with MPI, very well supported. It's a standard that really stands the test of time. It is very useful for point-to-point communication between the different cores, but you have also seen in the slides and also then in the video that essentially the idea is, of course, using much more processors in these parallel machines. So there, the collective operations that you learned will get incredibly important. And of course, they are very much dependent on how you define your communicators and how you identify those ranks you want to communicate with. So, of course, this is already then going, let's say, on a very fast pace. So let's come back a little bit, pull a break, and think about what we have to do when we think about the last time when we had the material about a C program, what we have now to do to augment a C program, essentially with MPI functions in order to get a parallel program. So let's go and think a little bit about what is really needed to go for this. And of course, when we want to start a parallel program, we have to have a cluster or access to a cluster. You have an account on Jötunn, so the most of you already. We will have soon one also on the deep clusters. So this is, of course, a key ingredient. You need somehow access to those systems. Frankly speaking, also, it's important to realize that essentially those systems usually have computing time allocations. So in many ways, on the big machines like jewels, you usually have to do a computing grant first, and you submit it outlining your scientific application, your basically outcome or desired outcome, and how many cores you need, how much memory you need, which application you're going to do. And when you specify this, you would say, essentially saying that you want to do MPI or basically shared memory, although as I said today, rather people combine this for really large parallel applications, but you will also outline the different libraries you need. And for sure, the first library we need to really start with the basics is an MPI implementation that you already learned from our previous practical lectures. And you can have this in our module environment, as you will see basically already in one of the earlier lectures, but also again today. Also take away the message what I present here in the second part is really a little bit tuned on our environment that we have for our assignment again a little bit. Of course, there are lots of different implementations. You don't have to use OpenMPI. There are others which MPI or also the deep systems, as I said, we're using Parastation MPI implementations. So with this, the idea is really thinking about now starting with the lowest level when you want to do parallel computing. And this is really using such a system, logging into it. Students again and again pointing out, yeah, but I can program in parallel, then ship over my basically parallel applications with SCP or something like this over to the parallel computer and then really use it there and then execute it there. However, I think the workflow gets more and more cumbersome. The higher basically you scale, the bigger your application will be. You have to have then parallel I/O to really get the throughput, a parallel file system, for instance, in this HPC systems, which then is really different from your laptop to really program against. So, but these are all advanced aspects of it. So let us look a little bit what is now behind the step one that you already realize is a very, let's say, trivial step to do to get to SSH. And also the second one you have already learned in one of our practical lectures, the last one where we had an idea of how to create really a C program and then compiling it. We learned something about the libraries include. We will learn that this is also relevant for MPI. But we also have learned the main, let's say, function, which always is alive, essentially, of this particular program that you do. In our case, we just use the printf hello world. That's not much of a logic, but at least something. And then the return value is often used to really say, was an error in the computing or was it successfully executed? If you remember, we were using then kind of as a next step, the C compiler to really get an executable that we can do. But now we have to think about that in our ways, our implementation means we have just a single version. Now, a single version of the C program should be done in parallel, could mean many different things. You could say, I have different programs that I will now do with C programs in parallel. It can mean I just use exactly this program that I just crafted and put it on different processors. And this is something what we call a single program, multiple data. Right, so this means that the same MPI program is actually then running on all the different processors, and everybody here in our example will do hello world. This is really the SPMD idea, where we start thinking parallel. Of course, no, immediately would think there's not really added value if you have 4 times hello world. What about, having perhaps this worker master paradigm where one maybe of the processor is collecting then data from all the others to report something? Computing in parallel with different ideas how to do this. You still can do this with the same program. You just have to identify the different processes to do different things in, let's say, an if clause or so. And for this is actually something what the rank comes later in very handy. The data exchange really has to do now, again, when we think parallel, in messages, right? We have no shared memory anymore across the different processors. So we really think as a programming model that I always have to send and receive something. Or as you have seen already in the previous lecture part or the video, I use a collective operation, which are not just point to point, which is then really involving many different processes for this message exchange. So we're using different building blocks with MPI, and these basic building blocks will come again and again too. Essentially, the building block is that we need parallel processors, but they actually also building up a so-called parallel computing environment. And this is a bit larger than just thinking about the processes we want to involve. Now, when we start with the basic building blocks, we always have kind of 2 variables which are kind of important to understand, and which is really then editing a text file using the C program, something which I also will demonstrate in our practical lecture 2.1. And then you augment a typical C program just with MPI parts. Now in the first part here, you see we want to have this interesting rank and the size, meaning the rank, what identity this particular execution of this hello world program is. Is it rank 1, 0, 9? And the size tells me something about the size of how many processors at all are actually working again with basically the same program, but with different executions on the different parallel processors. So, however, you see here also, it's just basically C only still, right? We just have to find here 2 variables in the C space, and we give them out as part of the printf statement. So no MPI specific part yet. We have to add this. In step 4, and what we do in step 4 is usually always very similar. We added here a header file in C, which means you have access to all the MPI functions. And we extend the C program again, and you would say usually that a valid MPI program is also the valid C program, right? So it would be strange if not. Hence, we also put it through the compiler. Otherwise, it would be not compiled. So these are properly defined ways how to use MPI in this kind of header files. And we make use of it again and again. Here are 2 examples. By using this header file, we can now start in creating this parallel computing environment that I said. So it's not just the processor, it's the hardware. It's also the software, the MPI computing environment here that we generate by actually starting with the so-called MPI Init, and that we close with the MPI Finalize. So, and you could say that everything what is related to MPI needs to be happening between these 2 MPI Init, and MPI Finalize. There's no parallel execution of code after it, and also not before the MPI Init. This is a very important part of it, which means the way how you program those programs is always very similar when you start from scratch. You always start with usually a rank and size and then directly put the MPI Init and Finalize before you do any application logic. So in many ways, you also would say you have already some construct and that you change them. Also here, my suggestion for the assignments and other parts is just use the simple C program we already have uploaded that you already know from one of the practical lectures and the assignment 1, and then just change and edit from there. Add the MPI inits, add the MPI finalize, and then of course also the different MPI statements that we're going to do in terms of really properly defined MPI functions. So when I do this with a kind of compiler, you can imagine I get an executable, but when we would have and done this, we have not really earned very much because still size and rank would be 0, would be not defined. And then it's actually not true what we're saying there. We could maybe execute it already on 10, let's say, different CPUs. But the point is here really, we need something from the environment to really fill it with some information. And this is where this parallel computing environment again comes in. It knows that basically we have, for instance, 10 processors received from the scheduler to work in. Essentially what you see here, right? So this is something what is known for the MPI COMM world. This is the kind of area of all the processes in. And we always can ask this with this interesting MPI function. What is the communicator size, which gives us actually the number of all the processes here, 10. And then what rank do I have? And this is usually with the students a little bit more difficult to understand. So I will repeat this for the rank because it's very important. Of course, once you also use it in the practical lecture in the assignment, you immediately get the notion of it. Think about, again, and this is now justifying the rank. Think about that this is now 10 times executed on the machine, right? Exactly the same source code with the executable we have compiled. So this immediately raises the question that everything is completely equal, as it should be, because it's the same program. But MPI enables you, by having the view on this parallel environment, to fill the rank with different identities. So think about that the rank really captures then the essence how you can differentiate between one execution and the other. So when I do this here, this program again, because it's a frequently asked questions in all my years teaching this, the same source code is actually executed on all of these in MPI COMM world. Let's assume we submitted to 10 CPUs with Hello World. All of them actually have the same source code. But the benefit of MPI here and the kind of benefit when using MPI COMM rank and filling this variable rank is exactly what you see on this basically illustration here, that your rank variable gets filled is different identity. And this will be in a way between all of these here on the Hello World, the only differentiator. Everything else remains the same. Of course, this is something we should do also in practice. As I said, we will do it in practical lecture 2.1. Parts of it are related to your assignment. Here you see a little bit how that works on our Jötunn environment. It's the same way. MPI COMM world, I have my size and the rank. The size gives me then how much nodes, or basically then how much CPUs I really have, or processes to be precise. And then from all of these processes, what is my unique rank in all of them in order to do something with it? How we do something with it would be, of course, naturally thinking about selection or an if clause. So I say, if rank 0, I do something. If I'm not rank 0, then I do something else. And this is a key paradigm in programming. Often rank 0 takes a special, let's say, role in the parallelization. But we will come to this, for instance, also later in this lecture when we think about a ping and a pong. Again, right, think about the ping and the pong should be different, executed, and we will come back to this shortly. Now, the way how you do it and use it then in step 5 is you have to load the right modules in order to compile. It's not that just a compiler is given. There are lots of different compilers in our world. There are different manufacturers that have actually MPI and C compilers. GNU you have seen. We have also, of course, then Intel, very vendor-specific ones. So all of this influence a little bit that before you actually really compile it, you have to think about in step 5 to load basically the right modules and then compile the C program. And you see that essentially here when I already do this kind of module load aspects that we require in order to even know what MPI here in the C program really means. So in other words, something what we already learned in lecture 01, right? We said there's a huge module environment. I can see all my modules with module avail, and then I have to use a specific modules that is relevant for me. In our example, we want to use OpenMPI, but with model Spider, we quickly found out when we modeled Spider OpenMPI that it has relationships to GNU because it's of course their compiler. So we have to actually also load GNU before we do the OpenMPI. So this is really important. Also a frequently asked question again from students, or a trap they often come into programming. They just think about the C program and they do the C program very well. But of course, think about that the C program is nothing with when there's not really the real module loaded for this particular problem. So in our case, that means you always, when you want to compile it, need to load these modules. In our Jötunn environment, this would be module load GNU OpenMPI. Once you have done this, you have it basically available in your shell, in your basically SSH session that you have in the shell. And when you do and quit this SSH session, and then you basically reconnect after some time, maybe you went away for lunch, for dinner, come back, and then relog in, of course, the modular environment is gone again, unless you maybe specifically configured it in a specific way, which we don't cover here in the course. But generally, you could say the module load is again away. So you have to again module load GNU OpenMPI, and then you can have access to the MPI compiler that you see here, the MPI CC that we already used. And then from this LOC, which is really a proper C program, now augmented really with MPI functions. And I'd say -O to really make an executor with a specific name. It's not required, but it's a bit more, let's say, clean of doing so. Once you've done this and there are no errors, which we here assume, then you basically have this interesting hello. And in Unix here in the file system, you see and can realize it always with the X here, which means standing for X for executable, while the other notions are read and write essentially for different levels of roles. Here, you also see already that this is not enough. I'm alluding here to our last lecture, which was about scheduling, right? The submit hello script. We're still going to use it only because we have MPI now in the kind of C program and augmented it with MPI. It doesn't mean that we don't have to use a scheduler or that the C program starting to do its own kind of submission suddenly to the scheduler because it's augmented with MPI. In a way, it's just the way how you program it. What we still have to do is to think about really submitting it then, this hello executable to the cluster. And that's, of course, something what we will do with one of the next steps. However, parallel processing is really a bit more complicated than that. So I cannot just, let's say, program it hard-coded inside somewhere of this MPI application that I have, the C program now augmented with MPI, and say it should be always running on the first 4 nodes available. Usually what to want to achieve is really that the amount of processors that you have in the parallel applications is not known. So you would never hard code it really for 4 or 8 or 12 processors. We talk about this of having basically inherent scalability. So in our world, in our example here, means we could execute the hello world on 4 processors as seen here, right? I have 4 times again the incarnation of having here this hello and hello world executed on different processors. But of course I can scale it to 8. We have seen the source code in the C program was never actually saying anything about 4. It was also not saying something about 8. This is something which comes through the job script. If you remember, there was a -n parameter in the batch part that I used also in the last lecture to show how many nodes I want to have. So this is important meaning. And in order to do this properly, there's a specific, let's say, counterpart, which is called MPIRun, which we will put in our shell scripts, in our submit scripts to the batch queue, that then will take the following. It will create, as you see here, in combination then with a scheduler that allocates this node, because they're now free for a certain user. Let's say they're free for me as Morris in the schedule. Then MPIRun will take care that now this executable we talked about, that we have actually compiled, that this is now distributed across the right and the correct processors. The right correct processors means those should be those where I have an allocation on, right? This is very important. I don't share my processors now with someone else. The scheduler blocked it for me exclusively, and I can use it now for 4 hello worlds. Saying also then that I cannot suddenly go to 8 hello worlds. It's not possible because the scheduler just has reserved 4 for me. Of course, on another submit, when I do, let's say, a highly scalable hello, I can ask for maybe 1024, basically where this will be then more than 1000 times executed. Of course, this has to do with the schedule. That means there needs to be free space for thousands to really be executed, but hello world couldn't care less. This kind of application has inherent scalability. All what it changes will have these 2 variables, size, and will always basically have the MPI environment to ask for, okay, I have actually 1000, or do I have just 4 overall? And then if you remember, we said there's a small distinction. They are all executing the exact same program, right? Single program, multiple data. So the multiple data in a sense means here in this very simple program that all of them have a different rank. So the rank data essentially is already different. And from that, you can also create, let's say, different flows of the computing. One very common paradigm is, for instance, a master worker, where you say rank 0 is maybe doing something else, which means you write in your hello program, if I'm rank 0, then please do this, else then do something else. And we will come to this again. Just to understand this in context of MPIRun is very important. You always do the same steps. That's why this lecture is really, in a way, a conceptual lecture, and will get in your blood much more when we have practical lecture 2.1, when we execute them, and then in the assignments. But still, the way how you do it is very similar like all the steps we had before. Even if you go to Fortran, you have to compile it. You use and basically an MPIRun to work with a scheduler together with SBatch in order to allocate actually resources. So that's why these steps, to know them, to understand them, is very important actually to do, to remember, and also the different parts of it. That's why we also will reveal again a little bit the job script in combination now with the MPIRun. So the last lecture already talked about this job script, and you have seen it's essentially nothing else than just a shell script, but with specific commands here in this part formulated as SBatch for the Slurm schedule to know a few things about your application. And what you will learn is that you can have a very nice fine granular setup of how many nodes you want to have, of how many tasks per node, and basically how many cores you want to get and receive. It's all something you can have here specified in the SBatch. You see, you get notifications from the scheduler. This is not only basically at the end of a job, it could be also a starting job and so on. So different ways how you do it. You should have usually a good proper name to do it. And you have, let's say, an indicator of the certain shell or basically that you use. I'm also convening again and again this, frequently asked question and trap, load the modules. So just because you compiled on this login node typically, right, when you do SSH and you do the steps we just talked, you were never going before to some of the compute nodes. Basically only in step 6, you really then MPIRun and then landing on all the compute nodes. In other words, when you module load GNU and OpenMPI already on the login node, right, where you do all the certain things of programming, you compile, that's fine. But when you want to have a real parallel execution across many, many, many different nodes, then of course you can do this really on the login node. This means your application needs to be shipped by MPIRun, as we learned, to these different processes. And this is, of course, something we have done the last time, now in the last slide. But what's here now important to understand is these are all blank processes. Blank in the meaning of you don't know that you executed a module load GNU OpenMPI on the login node, right? It has no connection. It's a completely different processor, has no idea that there's actually a module load required. Hence, you also have to do it in the job script. This is the reasoning why, although you actually specified this in your own login environment, when it actually is used with MPIRun, here the example that we have, maybe from the last year course, but it's the same way. It takes this executable, this MPIRun, that essentially you think it's lying on the login node, somewhere in the file system, but usually these systems have also parallel file systems, so it's a little bit more complex usually. But you can consider that the environment of programming is not the compute nodes essentially that then executing it. And hence I cannot say it often enough. Think about this as a complete blank environment, complete new environment. You always have to load there also all the modules you require for your application. Right, and this is always this kind of stepwise walkthrough that when you do this course, you will see you very much follow always this procedure. And after a while in this course, maybe already in assignment 2, it's already so clear known that you don't have to look that up anymore. You will again compile and run it, and then compile again, change something in the job script, change something in the C program, and then compile it again. So basically frequently asked questions again when I start talking about MPI is also if you will program Fortran in the course, and this is definitively not the case. We will look at one Fortran code in VARF very much to the end of the course, just to give you an example why Fortran is still there around, and actually show you also the fact that Fortran is still used. But of course, you program here just very simple C programs, as we already were clarifying before, just with the idea of understanding parallel computing and not being a complete expert in C, right? For this, you need years, you need lots of different more lectures of really understanding C. Yet you get every now and then a couple of ideas how a C program, of course, works. And you need to do this because, as I said earlier, also an MPI program is also a proper C program. Now, coming back to this all, to summarize essentially a little bit on all the steps, because we going towards the final steps here. You can imagine when you've done your parallel processing. So this is a step again. If you think about, you have this job script we just were pointing to, and we requested for 4 nodes. It's a very coarse-grained assumption. We could also have different, let's say, tasks only and CPUs only allocated. Here we have 4 nodes with a capital N, but it doesn't matter. It still shows you what the scheduler is doing. So when you have now basically just job script submitted, you get this unique job ID, which is very important, but you don't see any output. If you remember, we had hello world, I am 0 out of 20 or 50. Here I said it's out of 4, but I don't see any output. Again, like we had before when we were executing the normal serial one, also with the MPI, you have the same point that all of these output, even if it's now 4 times the output or 20 times or 50 times the output, you don't see anything on the screen. All the output is usually redirected to a certain output file. And if there are errors, there are even error files that are actually generated. And some of you will notice this when you have your first errors, let's say by typo or so, that it maybe compiles correctly, but if you run it, there's something wrong. Or a Cartesian communicator in your Ocean assignment that you will very soon work on is not really fitting to the amount of processes you specified in the job script. Let's say if you want to chop down an area into 12 pieces, and then you're executing it with, let's say, 3 processors, then it's a little bit unsure how the mapping is. There could be errors related to this, which we will come back also in one of the subsequent lectures. Once you have it executed, basically this sbatch command, it will land in this sbatch queue of the scheduler, in the Slurm scheduler queue, and to be waited to be executed once there are 4 nodes free. When then 4 nodes of this, let's say here in an example, 6 nodes are actually free, Then you essentially get scheduled on this exclusively, and your Hello World program is running indeed 4 times on these different 4 nodes, generating then, of course, all at once. That's a bit misleading term. And now the important part of power elements in it. Now, again, a frequently asked question and a trap. Please listen to me carefully now. We have 4 times this executed, and it, of course, gives you 4 outcomes. I am hello world, la la la, 0, I'm 3, I'm 2, I'm 1. But the output file is more or less a serial resource. Everybody wants to write into it, and basically then this output file gets augmented with another output, with another output, with another output. This is not really parallel I/O, it's serial I/O. And in the sense of this, we will see that the order, when you execute this in your assignments, will always change. It's basically just that, we have parallel executions and we don't know, one might be a milliseconds earlier ready than the other for some certain reason. And then basically the others have to wait to write to this file. That's why the order is very much dynamic in this different, let's say, executions. And if you do so, don't worry about this. In your assignments, it's still parallel execution, but the problem is that essentially this file has just, a serial part in it. And in subsequent lectures, we will learn that this is exactly a bottleneck, of course, for applications that want to run and write in parallel and want to have, let's say, more systematic matter of the output, right? We don't want to have maybe just a string that is given out here with hello world. In other applications, it's about particle positions and large arrays, for instance. There you want to have a concrete result in concrete array elements. And you basically use their parallel I/O. There are certain parallel file formats we will talk later, like netcdf and hdf5 in the course, but they don't matter right now. In the beginning of the course, think about that when you execute this and you hand in your assignment, don't worry that the order of these executions in your output files will always change and never be the same. Right, so we see this is drop to file inside actually your directory where you started the job. And for some of you, I already was saying, you maybe get also an error. So in this, you would find also maybe with the same job ID, and that's now the key point in this. You have to understand that this output file is related to this particular output of the job, because it could be very well that I maybe submit 5 jobs. I maybe submit 10 jobs at the same time. Why would that be useful? Maybe have different parameters. In our simple example, it could be hello world with 10 processors, hello world with 20 processors, whatever. Or in a different situation, let's say when you want to have an interesting particle collision example, or let's say you simulate stars outside the galaxies and want to understand their interactions, you maybe have it with basically with 10,000 of stars, with 20,000 of stars, then you maybe have 50,000 of stars, and you basically allocate more and more processors. I'm alluding to something we call parameterization of your simulation. It is not something directly only related basically then to your parallel environment, meaning that you maybe ask for 2048 cores, 2024 cores, whatever it is. It's also inside your practical application, right? And these differences will also get more clear when we talk about weak and strong scaling ideas, where you then change and keep basically on the one hand the application problem very static, but on the other hand keep the problem basically dynamic of really adding more and more detail and more complexity, like the number of particles, for instance. So with this, you come maybe to more and more realistic scenarios how you would do a parallel application. Okay, so much for the general use, why you basically decouple so much of these things. You would say we programmed a program, it's independent of the number of processors. With this, you can have an inherent scalability, but of course, we will see in the performance analysis then in this lecture that there's still some impact from the MPI message exchanges here. So you cannot just scale forever. Also MPI and the setup of the machines will have, of course, an impact in your scaling that we will also have later. However, it's very nice from the idea that you can nicely decouple this of not rewriting code, but basically have here an encapsulation by just having the job script then telling you how often this application should be executed. Right, so let's move on and really summarize this a little bit in order to understand really this parallel environment where message passing is living in. And this is a very important consideration where message passing is living in. We said already when we start with a typical C program, we have some life maybe of a C program even before, so we don't know that. Usually MPI include files is always at the tops, that's clear, but there could be some serial code, right? The program begins already, let's say, with the main function that we have seen the last time. There could be something what you just do, and it's serial. The parallel code really begins only if we have this MPI Init and, at the end, this MPI Finalize. And this is really your parallel environment. We're talking about the different processes which are now accessible. If you are basically before the MPI Init, you don't have any notion of a rank. You don't even know the size of how many processors you would have. So this is a problem. So how do you want to address another kind of processor? You need this MPI environment, which is then set up essentially to do the send and receive, to do broadcast messages, but also to understand really how many ranks I have in basically this particular communicator. Also here, you would do the real work of the applications. Here is something like really the practicalities of having parallel computing, of breaking a big problem maybe down into several different pieces. The ocean will be maybe simulated with 24 tiles, maybe with 12 tiles. Something which is, of course, then influencing the granularity, and things like domain decomposition become more and more important in this matter. This domain decomposition is not obvious to you. We will see how that materializes when we actually come to the next lecture 3. Before we will have some practical lecture 2.1 again to basically support your assignment a little with demonstrations. But lecture 3 is really all about domain decomposition. So thinking much more clearly the other way around. So when I come from the application perspective, how I chop up into different pieces. Here we started a little bit with the technical idea of how to do it, by really thinking about more message passing, more messages between the different processors and their environment. So having terminated then the MPI environment means you're back in the serial world. So there's actually no notion anymore of the rank that is valid, right? Even if you would say here's a processor and it is the same processor that you maybe have here, and here it is maybe very clear that this would be rank 0. It's not the case anymore because your whole MPI environment collapsed. You can still do, of course, C. You can maybe work with the parallel output and can work with the data here. And then basically you're back to a serial code. However, in practicalities, this is a very difficult statement to say and a bit provoking, because you would have something like load imbalance. And think about that the scheduler still thinks the job is not completed. So I still have allocated maybe 4 processors. So that means, in other words, the 4 processors are there, but just one processor is really using the time. All others, maybe 3 in the example here, they are idle. If they're not used, they're idle, and this is a very bad thing in parallel computing. Hence, we have load imbalance, also more basically discussed when we come to the theoretical implications of lecture 3. What do I do about it? What does it mean? And so forth. Here in our example, that would probably mean that you don't do much in the serial parts here and in the serial parts here. You keep a very well-balanced code usually, so that it executes and terminates almost at the same time, to not maybe have too much idle resources. Of course, also when you have a very complex program, and now think about the thousands of scaling in a program of processors, this is something where humans lose the connection really of understanding all of this. There's so many message exchanges that you need parallel performance analysis programs that can work at that scale to really help you understanding much more how the parallel execution is actually taking place. Now, this is a little bit the MPI environment, but once we have this environment, let us understand just briefly before we come to some interesting examples that we will also look in the practical lectures more, how now actually a package goes over the wire, you would say. right? So how I actually send now something from processor 1 to processor 2, and I was talking to you already before about this memory space is of course very important. Now, when I have processor 1, I have some data item to send in this, process A that I'm in, basically an MPI implementation like, OpenMP is here supporting in this environment. In processor 1, already one application could be our hello world, and we send the data hello world or so to another processor to give it out. Then we're talking about this message exchanges. And it could be a number, it could be a string like hello world, whatever it is we put over the wire. The important thing is here it's a variable, but it's also a variable in the processor 2, process B. So which means we have to allocate also space for this variable to receive it in the system buffer, basically while sending over the network. And this is essentially what MPI send is doing. And you see, I talked to you already about that when I'm sending something, I should be also able to receive something. So I should be listening. And this is what receive does also by preparing the data structure already of saying, I'm expecting a certain type of data. So you have always a matching send receive here in order to get this over. And because we're programming C, we really have to also allocate the variables for it on both the processes, on process A and process B, even if process B, of course, starts with an empty data item that then gets filled by this message exchange through the system buffer here, coming back into the application space. So this is already really technical. I just want to give you also some examples before we basically then have another video supporting a little bit ideas in Python, how you can use MPI for basically computing P. Here is the idea of how we use now send and receive. As I just was saying, again, on a very higher level view. And as I told you, one of the interesting examples with it would be this ping pong application that you already know from the assignment. It is a very trivial one, but it captures the essence of being ready, basically to receive when I have a matching send, right? In other words, I have here my program flow that you already very well know from this lecture, but I use a rank, the identity of these different ranks I have in a program. Even if I just ask for 2 processors, you will see with the number of processors I have 2, I have already different ranks. And say from my 0, I want to have it sent to 1. And then basically I can have my send routine that is essentially sending something to the destination, which is my ping. For this ping to work and to actually reach the destiny on the other processor, you have to have application logic that you differentiate with the F statement for our rank 1. So essentially the other processor here, living on this stream, has to be ready to get something. So hence, instead of send, we need first a receive. And the receive should be coming from a source. So the source here is, of course, rank 0, right? But this would be only a ping, right? So this would be the first incarnation you see here of a message exchange. We also want to have a pong. So the pong essentially would be saying, essentially I still the message. So literally ping and pong is actually not going over the wire here, to be honest, it's just an X, but it captures the essence of saying I first send something to be received by the other rank. And of course, now you can say, once I send something in the rank 0, I put myself into the receive state to wait if there's an incoming send. So that means they're changing roles here a little bit for the pong in order to say that the rank 0 is now the receiving one. And we see here with MPI sent to the destination 0, which is again the rank 0 where it should end up. This is something which then actually executes a pong, and because rank 0 is already ready for receiving, it will actually receive this pong and our application can go on. With get count, we see a little bit what's really going over the wire, and we can then actually prove that really something was going over the wire with this output statement that is also then better to understand when you really run it yourself, and when I also give the demo next time with practical lecture 2.1. So the collective function broadcast, of course, is one of the most used pairs I just shed light on very quickly. It's a different modus operandi, you can imagine. We said already we use the communicator for this message exchange much more, saying how many of these processes are all involved in the message exchanges. In our case, COMM world will be here just 4 in this example, and that's why I basically do just here a kind of loop between all the different let's say ranks which I want to fill, basically, but only saying in the application logic again that I'm ranked 0 here in the first place. And then I will do this broadcast once, right, to all the other processors in the MPI COMM world. That's very important. And then essentially you kind of have the buffer here then also, let's say, given out so that we really can understand that this is basically coming and then receiving what we get through all these message exchanges, because the initialization of the buffer with the numbers here will be just happening for rank. All others would be undefined. But as we execute this 4 times, or maybe 8 times, or 200 times, it doesn't matter then. Of course, you would have then the point that essentially only with this you can prove if all the other processors really get something from the broadcast. This will be also demonstrated in practical lecture 2.1 when we have the outcomes. So I really skipped that here because it's also part of your assignment to really do it yourself. And really, also we'll look a little bit into this together in lecture 2.1. So that's all essentially also for the kind of more conceptual MPI lecture today. And this really was something which really sheds you a little bit light on MPI. It's a very powerful standard, very good implementations, strong since 1994, as you have seen in one of the videos. And here you see another operation, all gather, that is in this video, which I found quite useful in this video to show you. Of course, also there is the idea of comparing serial versus parallel computing P, which is also interesting by using the Python environment to get you a little bit a broader perspective. But take away the message that usually parallel programming with MPI are 3-day courses, 5-day courses. Your whole university lecture you in a way could do just on using MPI and ignoring GPUs, ignoring shared memory. This would be still a lot of material inclusive, of course, of parallel I/O. But this is a high performance course, so we have a much broader perspective. MPI is just one part of it. But let's look a little bit on the video before we close today, because it captures quite nice elements.
Final section, we will take a closer look to collective communication. MPI includes several communication patterns for collective communication. The first pattern of interest is broadcasting. This is the case where one process will send a message to every other processes inside the communicator. A second pattern of interest is scatter. In this case, one process will split its message into several parts and send individual parts to different processes. A pattern related to scatter is gather. It is the inverse process of scatter, where different portions of a message are put back together from several processes. An extension to gather is the MPI allGather, where the gathering process is done for all processes. In this mode, each process ends up with the overall information. MPI also includes collective communication methods to merge values from several processes. For example, the function MPIReduce reduces several values to a single value. The function will apply a reduce operation. In this example, the reduce operation is MPISum, which simply sums all values into a single value sent back to the process 0. Many other reduce operations can be applied, including min, max, product, the logical AND, etc. To illustrate how to use collective communication patterns, we will proceed with the example of computing pi. There are many algorithms to compute pi. In this example, we will use the following approximation using a summation. As we will increase delta x in this formula, we will get closer and closer to the real value of pi. As you can imagine, as we increase the number of steps in this computation, the longer it will take to be computed, especially in a serial manner. In such a case, it is possible to split the summation over multiple processes to accelerate the computation. So first, let's compute pi in a serial manner. This will be done by simply looping over the number of steps and updating the summation result each step. Finally, we evaluate pi. We also evaluate the computation time and report it at the end. So let's look how long it takes to compute 100 million steps. In this case, it took about 30 seconds to compute on an interactive node on S star. Now, let's build our MPI version. As usual, we first collect information about the MPI COMM world to retrieve the rank and size of each process. We also evaluate the number of steps that will be handled by each process and compute the start and end boundaries. Then, each process will compute its section of pi in the for loop. The main difference here with the serial version is that the loop will become smaller and smaller as we add processes. This is a classic divide and conquer method, common in computer science. Finally, for this function, we return the partial sum. What remains to be done is the main function. Here, we make use of the MPI reduce function. In there, we will execute the function that we just defined in the previous slide with all available processes and apply the reduce operation sum. Once everything is complete, we will print the result. And that's it. Let's now execute this code to see if it's faster than our previous test. And, indeed, while splitting over 14 processes, it took only about 6 seconds.
Right. So this was really a lively demonstration, I think, which shows you a couple of good things. The first was all gather, also incredibly often used in many applications because you have the results really available again on all the processors. And also you have seen a little bit about, using it with a, let's say, very trivial mathematical function of approximating pi actually. So computing pi in this kind of idea of serial was very simple, and also the parallel was admittedly not really complex, but still captures the essence how you basically can do parallel computing. And now you have to imagine that, of course, larger applications in the domain sciences are much more complicated than we have here, like computing pi. But it shows you, that these problems will be always very similar tackled. They chop down a big problem and a divide and conquer, what also was mentioned in the video, to, let's say, a smaller number. And the smaller number usually depends on how many processors you ask for. In some other applications, it's maybe more the memory you ask for because you have more memory bound applications, which basically limit your behavior of applications. But this is something we will see in later lectures. We stop here for a practical lecture 2.1 coming up at the end of this week. And yeah, thank you very much for being part of here, and see you then at the next lecture.